So our objective in this topic is to understand the concept of what is angular momentum of a particle and apply the equation of angular impulse and momentum. We will also study about conservation of angular impulse and momentum to solve the problems. So before we talk about angular impulse and momentum, let's revise what is linear momentum. So when a particle with mass m has linear velocity v, then the linear momentum of the particle is the product of mass and velocity, which is given by L is equal to m multiplied by v. So linear momentum is because of the mass and linear velocity of the particle. Similarly, angular momentum is because of the mass and rotational motion of the particle. You can see in all these examples, particle has rotational motion. Look at the flywheel in first case, rotating gears in second example, satellite orbiting the earth, or amusement ride. You can consider all the riders as particles with certain mass and they are rotating with respect to the axis of the amusement ride. So they all have angular momentum. And this nice spinning top from Inception, this is also has angular momentum. So so angular momentum depends on the mass and angular velocity of the particle and the distance of the particle from the axis of rotation. That means in the amusement ride, the angular momentum of a rider changes depending on how far the rider is from the axis of rotation. Having said that, all these planets in our solar system, they have angular momentum because they all rotate or orbits the sun at some distance. Look at this figure skater. He is also he also has angular momentum. Careful, pay careful attention to his body language. When his arms are closer to his body, he spins faster compared to when his arms are spread, he spins slower. This is an interesting concept and we will come back to that point later in the class. So what is angular momentum? How do we define it mathematically? So angular momentum is a moment of linear momentum about the point or axis of rotation. Again, I repeat, angular momentum is a moment of linear momentum about the point or axis of rotation. So in order to derive the equation for angular momentum, we should first understand how to calculate the moment in 2 dimension and how to calculate moment in 3 dimension. We have already studied this concept in statics, chapter 4. I have one slide from chapter 4 as a quick revision of how to calculate moment. So when a force F is applied, you can see it at my cursor, at some distance from the axis of rotation, then the product of force and the distance from the axis of rotation is called the moment. The unit for moment is Newton into meter if it is SI system, or if it is feet pound if it is FPS system. When the force and the distance vector are in the same plane, then it's called 2D moment, which can be easily calculated by multiplying force with the distance. If the moment is in 3 dimension, that is the position vector is combination of x, y, and z components, and force vector has also x, y, and z component, then the moment can be calculated using a cross product. Here MO stands for the moment of force about point O, which can be obtained by cross product of R with F. So this is R cross F. And we have studied in statics that R cross F is not same as F cross R. In fact, R cross F is negative of F cross R. The magnitude of the moment can be calculated using the determinant of a matrix as shown in this slide. In chapter 12, we have studied about rotational motion of the particle. So when particle goes through a curved motion, At any given instant, the velocity of the particle is tangent to the curvature and it points in the direction of motion. So this is the velocity vector for the given instant of the particle. If this particle has mass m, then we can say that at the given instant, particle's linear momentum is product of mass and this velocity. We have seen in the previous slide the angular momentum is a moment of linear momentum about the point of rotation, and here point O is the point of rotation. So if we apply the same concept of moment that we applied in case of force and distance to calculate the angular momentum, then it is the cross product of vector r with linear momentum. So this is r cross mv, and that's the equation for angular momentum. So the angular momentum of a particle about point O is defined as the moment of the particle's linear momentum about point O. You can see in this example that particle goes through this curved path in xy plane. At the given instant, linear momentum of the particle is mv, and the position vector from O to the particle is given by r. Then angular momentum of the particle about point O can be calculated using r cross mv, where r is a vector, mass is scalar, and velocity is vector, so as the angular momentum. So we use letter h for angular momentum, and O indicates angular momentum about point O. The magnitude of the angular momentum can be determined using the determinant of a matrix, where the first row I, j, k are unit vectors in the direction of I, x, y, and z axis. Second row are three elements of the position vector respectively in x, y, and z. And the third row are the elements of velocity vector multiplied with mass in x, y, and z. You have studied in statics how to calculate momentum, how to calculate the determinant of the matrix. If you need the equation, it will be provided you in the equation sheet. And the magnitude of angular momentum in this example is mv and d. So h0 here, ho, is both magnitude and direction, while the only magnitude is mvd, where mv is the linear momentum and d is the perpendicular distance from point O onto the line of action for mv. Let's look at this reading quiz. Select the correct expression for angular momentum of a particle about a point. So you know that equation, the correct answer is r cross mv, option B. Read the second question. The sum of moments of all external forces acting on a particle is equal to, and we have four options, and you will shortly notice that the correct answer is time rate of change of angular momentum, that is option C. What are the applications of angular momentum? Planets and most satellites move in elliptical orbits. This motion is caused by gravitational attraction forces. Since these forces act in pairs, the sum of the moments of the forces acting on the system will be zero. This means that angular momentum is conserved. If the angular momentum is constant, does it mean linear momentum is also constant? Why or why not? So let's study this situation. In this example, there is gravitational force between the satellite at point B and the Earth, and it's the same gravitational force between satellite at point A and the Earth. Now these forces are equal in magnitude and opposite in direction, so there is no net force acting responsible for the change in angular momentum. So angular momentum at point B is same as angular momentum at point A. At B, the angular momentum is the product of r cross mv, and at A, it's also the product of ra cross mva. Now, in both the cases, mass of the satellite does not change when it orbits the Earth. That means the velocity depends on the position vector. So if the position vector is shorter, then velocity will be higher. And when the position vector is long, then velocity will be small. That means as the satellite moves away from the Earth, its velocity decreases. So that is the answer for the first question, that what is the angular momentum or what is the velocity. So if the angular momentum is constant, does it mean that linear momentum is also constant? And the answer is no, because the linear momentum is the product of mass and velocity at B is not same as velocity at A. So linear momentum is not constant. In fact, it is the same concept that is applicable to the figure skater. So figure skaters, they bring their arms closer to their body, thereby they reduce the distance from the axis of rotation, and that increases their angular momentum. And when they spread their arms away from their body, it increases the distance from the axis of rotation, and their and their velocity decreases and their motion slows down. Another application of angular momentum is in amusement ride. So in the amusement ride, if you consider a rider as the particle, then each particle rotates at some distance from the vertical axis of the amusement ride. Now the particle has fixed mass, hence the velocity of the particle depends on the distance from the axis of rotation. So particles or the riders which are close to the axis of rotation, they have less velocity, they have higher velocity compared to the particles or the riders which are away from the axis of rotation. In this example, however, there is no contribution of weight or the normal force acting from the seat for the angular momentum, because none of these forces generate any moment about the z-axis, which is the axis of rotation. Because the normal force intersects with the z-axis, net moment is 0. Similarly, weight is parallel to the axis and the moment is 0. We have studied in statics that when a line of action of force intersects with the axis of rotation, then there is no moment. Similarly, when the line of action of force is parallel to the axis of rotation, in that case also there is no net moment. So the question is, if the passengers move away from the z-axis, will his speed increase or decrease? And we have already answered this question, that as you move away from the axis, the speed decreases. This is the same equation that we have studied in section 15.1, that is the equation for the linear impulse and momentum. It is just the another way of writing that same equation. So if you remember, we had mv is equal to sigma f multiplied by dt. So that dt, if you divide it on the right hand side, then it is the derivative of velocity with respect to time. So as per this equation, sum of all the external forces acting on the particle is equal to time rate of change of its linear momentum. As per this similarity, sum of all the external moment acting on the particle about point O is equal to time rate of change of its angular momentum about that point. Now this slide explains when we have more than one particles, then we have to consider sigma h, that is the sum of angular momentum of all the particles. So once again, I'm comparing linear momentum with angular momentum to write the final equation. So we have studied the first equation, which explains that initial linear momentum, sorry, there is a typo here, mv1 plus linear impulse is equal to final linear momentum. With similarity to angular momentum, the equation is initial angular momentum plus angular impulse is equal to final angular momentum. h01 is initial angular momentum. m0 dt is the sum of all the moments, integral of all the moments with respect to time. and HO2 is the final angular momentum. So now the next question is, what is the unit of angular momentum? You can pause the video and think about it from this equation. You know the unit for moment, that is Newton meter, and you know the unit of time, which is second. Hence, one unit for angular momentum is Newton meter second. And you also notice that angular momentum is the product of mass, velocity, and distance. So second unit for angular momentum is kilogram, velocity is meter per second, and the distance is meter. So the another unit for angular momentum is kilogram meter square per second for SI system. So two units for angular momentum, Newton meter second or kilogram meter square per second. For FPS system, it's feet pound second or slug feet square per second. Let's apply this equation to a practical situation. This is the hand start engine. So look at this example of hand cranking of an engine. So the engine contains in this machine there is a pulley which is attached with the crankshaft of the engine. There is a lever which is attached to the pulley. So initial angular momentum of the pulley is 0 because there is no motion. Now when a person pulls the lever, he applies moment to the pulley. So he applies force at some distance away from the axis of rotation. That results in moment. So net moment will change the final angular momentum of the pulley and pulley starts spinning. So this equation, as per this equation, initial angular momentum of the pulley is 0. This middle term is the angular impulse applied by pulling the lever, and that results in rotation of the pulley with some final angular momentum. We have already talked about the units. Now let's talk about the direction. What is the direction of angular momentum? So angular momentum is a vector, so it has both magnitude and direction. Look at this example where two balls are attached on the lever and they are subjected to external moment at the center as well as couple forces at the ends. As a result, the final angular momentum of the system is different from the initial angular momentum. The entire system spins counterclockwise into this plane of slide, and angular momentum is perpendicular to this slide and coming out from the slide. That is the direction of the angular momentum. To find the direction of the angular momentum, you can apply the right hand rule. You can take your right hand and curl the fingers of your right hand in the direction of rotation, and the thumb points towards the positive direction of the angular momentum. We have already seen this equation. It is just rewritten in a different way. So this equation is called the principle of angular impulse and momentum. And now we'll talk about the conservation of angular momentum. So when the sum of angular impulses acting on a particle or a system of particle during the time from t1 to t2 is 0, then the angular momentum is conserved. That means there is no angular impulse. Angular momentum at the beginning is same as angular momentum at the end. So h01 is same as h02. When there are more than one particles, and this equation is very similar to conservation of linear momentum that we have studied, that is sigma mivi1 is equal to sigma mivi2. And this equation is applicable to the satellite example, and it's also applicable to the amusement ride example, that angular momentum of the particle is same at point B and at point A. That means velocity at point A is less than velocity at point B because the position distance of satellite from center is higher from point A compared to point B. So velocity is inversely proportional to distance when the angular momentum is constant. Higher the distance, lesser will be the velocity. So this is the summary of equations that we have seen so far for angular impulse and momentum. So the first equation is initial angular momentum plus impulse is equal to final angular momentum. And the second one is conservation of angular momentum when the net angular impulse is 0. In both these equations, h is angular momentum. If the system is two-dimensional, then the angular momentum can be calculated using product of mass, velocity, and distance from the axis of rotation. And if it's a 3D problem, then we need to go for vector solution, and angular momentum can be calculated using cross product of position vector with mass and velocity.